Okay, and share screen. Okay, so let me first quickly review what we discussed about the Dirac theory, and a part of that has to do with the homework problem. So you might have questions about it. So the Dirac invented this idea, starting from the observation about the Klein-Gordon equation. It didn't allow for the probability interpretation, and of course, we now know how to deal with it, namely that we regard this as the field theory instead of quantum mechanical wave equation, and quantize it and get the spin zero particles out of it. So we know how to use it now, but Dirac didn't back then. So that's why he tried to come up with a wave equation that would allow for probability interpretation in the standard quantum mechanics fashion. But of course, he wanted to have the equation that's consistent with the relativity. And to be consistent with the probability interpretation, it has to be the first order differential equation in time. And to be consistent with relativity, you need to treat space and time on equal footing. And therefore, the spatial derivative also has to be the first order in the wave equation. So that's how he came up with this ansatz of what equation should look like for the quantum mechanical wave equation. So that's the analog of the Schrodinger equation, now being consistent with the relativity. But in order to do so, he had to introduce these coefficients, alpha and beta. And for this equation to be also consistent with the relativistic relationship between the energy and the momentum, so he needed to have these coefficients alpha and beta to satisfy these anti-commutation relations, namely that two different alphas anti-commute, and they square to 1 when they are the same. And same with beta, and alpha and beta also anti-commute. And there are no numbers that satisfy these requirements, so that's why he had to actually go for matrices. So alpha and beta turns out to be 4x4 matrices, so that the Hamiltonian, which is the right-hand side of this equation, is now written in terms of the 4x4 matrix form. And of course, P is meant to be the derivative operator, just like on the previous slide, but this is now incorporated in by 4x4 matrix. And you are verifying this in your homework problem. So when you take this Hamiltonian and compute the commutation relation between Hamiltonian and the orbital angular momentum x cross p, x doesn't commute with this p, so that gives you IH bar. So HL commutator turns out to be this, which in then means that the orbital angular momentum is not conserved under this Hamiltonian. But if you put in another matrix sigma, and where you can also verify this commutation relation, you'll find that this combination I equal J, which is the orbital angular momentum, plus H bar over 2 times this matrix sigma, turns out to commute with the Hamiltonian. So this is actually a conserved quantity. So what this suggests is that in addition to orbital angular momentum, you need to combine it together with this matrix angular momentum, whose eigenvalues are plus minus h bar over 2. And therefore, we regard this to be the spin of this particle. So if you take this wave equation, then it would actually describe spin 1/2 particle. So that's what Dirac pointed out. We also verified that it has the correct non-relativistic limit. And in the non-relativistic limit, of course, the energy is supposed to be dominated by the rest energy mc squared. And the deviation from mc squared is the kinetic energy piece, which we call E prime, which can be ignored relative to 2mc squared for the lower two components. But for upper two components, mc squared cancel between the left and right-hand side of the equation. So you can isolate this E prime piece for the upper two components. So as the end result is that the upper two components now satisfy this equation, which really suggests that this is the kinetic energy of the non-relativistic particle. So it does lead to the correct non-relativistic limit. So we wanted to verify that. And then you are doing in a homework problem right now that when you actually couple this also to the vector potential, you find that it actually predicts the correct magnetic moment, namely the G factor 2. And when you actually work this out, it may be actually useful to know these identities for the Pauli matrices. So Pauli matrices satisfy this anti-commutator. They also satisfy this commutation relation as well. And when you actually look at this piece here, when you have one factor of sigma matrix, another factor of sigma matrix, and they may come with a different components, what you want to work out is the product of two sigma matrices. And sigma I, sigma j can be written as a half of the anti-commutator plus half of the commutator. Because in the anti-commutator, I have sigma I, sigma j plus sigma j, sigma I. In the commutator, I have sigma I, sigma j minus sigma j, sigma I. So the ordering of the sigma j, sigma I cancels between anti-commutator and the commutator. But the first ordering of sigma I, sigma j would add up with 2 halves to 1. So this is the way you can rewrite the product of two sigma matrices in terms of anti-commutator, which is delta ij, and commutator, which is now a single factor of the Pauli matrix. And the piece that becomes delta ij gives you this first piece, which is the kinetic energy. And the piece with the commutator, which can be written in terms of this epsilon tensor, would turn into the magnetic field, because two components of P minus EJ actually don't commute. Their commutator actually turns into the magnetic field. So that's how you can actually work out this G factor 2 if you haven't done this yet. So this is a hint I'm giving you right now that if you are struggling with how to work out this product of two Pauli matrices, this is one way you can actually simplify the algebra and to get this expression you are being asked to derive, which leads to the prediction that G factor is 2. Any questions about this algebra?
How exactly do we get the product of the Pauli matrices? If I understand correctly, we just have the dot product of the sigma, the Pauli vector of matrices, and then our covariant momentum. So we have that whole squared, right?
Right. So you can write this as sigma I, P minus EA I, the I component of this covariant derivative, sigma J, and P minus EA J. And of course, repeated indices are supposed to be summed over, the Einstein's convention. And you first write it that way. And of course, sigma would commute with P minus EA. So I bring this sigma J up front. But sigma J doesn't commute with sigma I, so you have to keep the correct ordering. That's when I use this identity to write sigma I times sigma J in terms of anti-commutator and commutator. Anti-commutator now turns into half times 2 delta ij, so this delta ij. So I and j indices are not the same, and you sum over them, so that turns into P minus EA I and P minus EA J with delta ij summed over, and that gives you this P minus EA squared. So that's this anti-commutator piece. But the other piece is this commutator, and again with a half, that cancels factor of 2, so I have I epsilon ijk sigma k. Now you need to work out epsilon ijk, P minus EAJ, P minus EAI, P minus EAJ. And epsilon ijk is totally antisymmetric. So P minus EAI, P minus EAJ, I can antisymmetrize it and write it as a commutator of P minus EAI, P minus EAJ half. And that commutator picks up the piece where P is the derivative acting on X. That's an argument of A. So that gives me DI-AJ. But you also have the piece that AI and PJ commutator, and that turns into minus DJ-AI. So if you put both of them together, that turns into curl of A. And that's how you end up finding the magnetic field. So that's why you can use this identity to rewrite this product of two sigma matrices in terms of delta ij and this epsilon ijk sigma k. And this epsilon ijk sigma k piece turns into commutator of two different components of covariant derivatives that it turns out to be the curl of the vector potential and hence magnetic field. And the rest is just know that sigma is twice spin. And I think I forgot a fact of h bar here. So I should have actually put h bar back in here. And h bar sigma over 2 is the spin operator. And that's how you end up with this expression at the end of the day. Does that answer your question, Sahil?
Yeah, yeah.
Hopefully you can do this in the next few hours. All right, any other questions on this point? Is everything okay? Good. So anyway, this was a little hint that might help you to finish up the homework problem. And the another part of the homework problem is to look at the solution when momentum is 0. Namely, we're talking about particle at rest. So in this case, the first term in the Dirac equation vanishes. And the second term is mc squared times this 4x4 matrix beta. And the beta has two eigenvalues 1, two eigenvalues -1. So if you're looking at the upper two components, then the energy eigenvalue is clear. So IH bar ddt is the energy, which turns into mc squared. So I have two solutions in the upper two components where energy is mc squared as expected for a relativistic particle at rest. So it's really the rest energy as Einstein's equation of E equal mc squared. So that's good. But we faced the other solutions, looking at the lower two components. And because this minus sign, I have now a solution with energy being negative mc squared. So we find solutions whose energies are negative. And we will actually solve this equation for a finite momentum later on today. So we will have the full scope of solutions you're going to see later. But the upshot here is that whether momentum is 0 or finite, it doesn't matter, because this equation would square, was designed this way, to the energy squared being p squared c squared so m squared c to the fourth. That's a requirement Dirac made to come up with this equation after all. And when the requirement is energy squared being p squared c equals m squared c to the fourth, then of course, when you take the square root of both sides, you find both signs as a solution for the energy. So ultimately, this is the origin of negative energy solutions. So it turns out that there's no way out of this. You do find negative energy solutions, and that's the problem Dirac actually struggled with. And any questions on this slide? We went through this last time, but it's been a week since then. Is this okay? And you will see the explicit solutions with finite momentum later on. Okay. So now that you have these negative energy solutions, there was a big concern, namely that if you have an electron with a positive energy, it may decay into a negative energy solution. Then no electron turns out to be stable, and they keep falling into these negative energy states, and so that would be a problem. So the trick Dirac came up with is to say, well, okay, we got these negative energy solutions. We don't want a positive energy solution to decay into the negative energy state. So let's say all these negative energy states are already occupied. If that's the case, then positive energy state cannot decay into negative energy state because it's already occupied by the Pauli exclusion principle, which we decided to call Pauli diversity principle. So that's the way he managed to avoid this catastrophe with his equation. But that solution came with a cost, because now, in order to make this positive energy solution stable, you have to occupy all of these negative energy states. He wanted to come up with a single particle Schrödinger equation made relativistic. But now it doesn't allow for such a simple interpretation, because now you have these infinite particles occupying the negative energy C, he called. This is what is called Dirac C. So he managed to solve this catastrophe. Positive energy states now don't decay. They are stable, which is good. But the cost is now you have to face this infinite body problem. So interpretation as a single particle quantum mechanics equation now miserably failed once again. So the Klein-Gordon theory failed because it didn't allow for probability interpretation, and we had to go to quantum field theory. Dirac equation now failed because you have these negative energy solutions. You have to occupy them. Then you have to deal with this infinite body problem. And once again, we have to go to QFT for this purpose. So again, relativistic quantum mechanics doesn't exist. So we talked about two attempts. The first one was Klein-Gordon equation. It failed because of lack of probability interpretation. The second attempt to make it consistent with the probability interpretation by making the equation first order differential equation both in space and time. But now that you have these negative energy solutions, you have to again go to quantum field theory at the end of the day. So all efforts trying to come up with relativistic version of quantum mechanics didn't succeed. But instead, we now know quantum field theory from non-relativistic Schrodinger theory, and we are now applying the same QFT now with these relativistic wave equations as field equation instead of quantum mechanical Schrodinger equation. And using them as a field equation, you have a consistent quantum field theory that will lead to the well-defined Hilbert space. So that's why we have to go to QFT. But another important thing we learn here is that you have to occupy all of these negative energy solutions and making sure that the occupied state can no longer accept additional particle in it. And that is achieved by Fermi statistics. So what we learn here is that for the spin 1/2 particle, it has to be a fermion. And that's what we talked about in spin statistics theorem. So the spin statistics theorem tells you that the Klein-Gordon theory, which has spin 0, had to be quantized as a boson. Now we learn that the Dirac theory, which has a spin 1/2 particle, has to be quantized as a fermion. And whether you would use Bose statistics or Fermi statistics was an option in non-relativistic Schrodinger field theory. The same Lagrangian could be quantized either as a boson or fermion, and you didn't have any requirements on which one you were supposed to take. And in addition, there was no correlation with spin when you choose a particular way of quantizing it. So it was just something you had to pick on your own. But now we learn that no longer such a freedom exists once you actually combine quantum field theory with relativity. So you are now forced to use Fermi statistics for spin 1/2 and Bose statistics for spin 0. And we also know that for the photon with spin 1, you are supposed to quantize as a boson. So that's the content of spin statistics theorem. Now we have a well-defined prediction that integer spin particles have to be bosons and half-odd spin particles have to be fermions. Okay, so that's one conclusion we learned from the relativistic QFT. Any questions about this point? Again, this is the review of the last time, so probably you are already getting sort of familiar with the statement. And that led to this observation that the antimatter is now being predicted once again. So we have seen that in Klein-Gordon theory. We are seeing this again in Dirac theory. And the prediction from Dirac theory actually came out first, chronologically, in the history of the development of the quantum field theory. So now that we assume that all the negative energy states are already occupied, we can talk about a hole. So if one of the negative energy states is not occupied, this appears as a hole, as we talked about with the Fermi degenerate system in condensed matter systems like metal. And we learned that hole would actually give you a particle of the same mass, but opposite charge. And you use this observation in the midterm exam, where you looked at, for example, the halogen atoms, like fluorine or chlorine, and you can view these electronic states of the halogen atoms as a whole in the outermost p orbitals, and you observed to understand the spin of the atom of being 3/2, you have to revert the sign of the spin-orbit coupling. And that was a sign that the hole carried the opposite charge from that of the electron. So this is where you actually use this idea that the hole of unoccupied state can be viewed as a state with the opposite electric charge. And we are applying the same idea here. And so that's the prediction of antimatter. That in the case of atom, that was a description of convenience. Rather than talking about 5 electrons in the p orbital, it's much easier to talk about one hole in the p orbital, and that has the opposite electric charge. But here we are talking about the universe. So we are talking about this relativistic quantum field theory, where all these negative energy states are occupied in our empty space out there. And if you have a hole in this negative energy state, and that's a particle you can observe with opposite charge, but of the same mass, and that's a projection of the positron, positive electron. And that's something that Carl Anderson indeed has discovered in 1932. So this is the picture, which is published in the paper. And the title of the paper is indeed Positive Electron. The name positron came later. So the title of the paper was Positive Electron, which is what Carl Anderson discovered using this cloud chamber. And cloud chamber is filled with gas, which is in this sort of supersaturated state that whenever some impact is made on the gas inside this chamber, then it becomes a droplet into the liquid form. So this is actually what is shown in this trajectory here. When a charged particle goes through this gas, then it quickly makes this vapor, a liquid, on its way. And that's something you can observe by taking a picture of it, because the droplets would reflect light. So that's the picture taken here. And the trajectory is curved because of the magnetic field from Lorentz force. And do you know which way you apply the magnetic field? Because that's what you have done intentionally. And at this stage, you may have ambiguity in the interpretation. It may be positive particle traveling this way, upwards, or maybe negative charged particle traveling downwards. In the same magnetic field, you can have these two ambiguous interpretations. So Lorentz force for the positively charged particle moving this way would have the force to the left. So the particle would bend this fashion, going upwards. Or negatively charged particle coming downwards, the velocity is now downwards. Charge is also opposite, and the force is the same as before by the Lorentz force, because it's V times charge cross B. So that's also a force towards the left. So trajectory would also bend this way and going downwards. But he was very clever. So he had this metal plate right in the middle. And what you see is that the curvature of the trajectory is more curved in the upper half of this picture than the lower half. And Lorentz force would bend the particle. And if the particle is moving slowly, then it gets bent more. So what this picture is showing then is that the particle has higher velocity in the lower half of the picture and lower velocity in the upper half of the picture. And the change in the velocity happened when the particle went through this metal plate. And when the charged particle goes through a metal plate, all it can do is lose energy. It doesn't gain energy. So then that leads to now unambiguous interpretation that the particle started out below the metal plate when it had a high velocity, went through the metal plate, it lost energy, and now that particle has lower velocity, it bends more due to magnetic field, which then uniquely points to the interpretation that it is a positively charged particle coming from below, losing energy in the metal plate, and keep moving above. And so this is a positively charged particle. So thanks to this metal plate, he could come up with this unambiguous interpretation that this is a positively charged particle. And knowing some rough idea on the energy of this particle, he would exclude the possibility that this is a proton, because the proton and electron have totally different charge to mass ratio, and their trajectory will be very different from each other. And electron loses energy a lot more inside the metal plate than proton does. So the change in curvature is consistent with the interpretation that this is the particle of the same mass as the electron. And at this stage, it was not a very accurate measurement. So it was consistent with the same mass as the electron, but nonetheless, it was inconsistent with the same mass as a proton. Hence, the interpretation of being positive electron. So that was the discovery of this, by Carl Anderson from Caltech, of this the positively charged particle, which people were not aware of before, but now he discovered it, whose mass was consistent as the same as the mass of the electron. So that was the discovery picture in 1932. Any questions about this?
I just had a question how we can, or I guess in the case of a hole, it's pretty obvious that it would have opposite charge because we are dealing with charged particles and it would make sense in that scenario. But how do we arrive at that conclusion in this Dirac interpretation of opposite charge and same mass?
Yeah, so it's the same argument as you have done in the piece of metal in condensed matter physics, and also in the case of the halogen atom with the p orbitals. So if you have a vacancy in the negative energy states, which are supposed to be all filled, we regard the empty space, outer space, to be this situation of all the negative energy states, namely that only when all negative energy states are filled, we say there's nothing. So that's a definition of nothingness. And relative to nothingness, that's what we call the vacuum, you have removed one electron. So relative to charge 0, which is meant to be the nothingness, I have removed one electron, which has a negative charge. So now the vacuum has now acquired a positive charge. So that's why we interpret this hole to have a positive charge, which is the opposite from electron. Does that answer your question?
I see. So it comes in a pair, basically. If
That's
you want
right.
to pull a particle out of the sea, you have to create antiparticle and particle pair.
That's exactly right. So if you actually send in a photon, for example, to excite one negative energy electron to a positive energy electron, then you have one hole and one particle occupying a positive energy state. So you observe one positron and one electron. And in that way, the charge is, of course, conserved. When you send in a photon, you're not providing electric charge to the system. But when you create a positron and electron together, then charges cancel against each other. So the charge is still conserved, starting from 0 charge initial state to 0 charge final state. But nonetheless, you have created matter out of energy, namely that you have one electron and one positron. So that's the idea of the pair creation of matter and antimatter. Thanks for asking that question. Any other questions at this stage? Does this picture make sense? Okay. And as we just talked about, when you send in a photon and excite a negative energy electron to a positive energy state, that is the phenomenon of pair creation. So this is the first ever antimatter created by humankind by sending in a gamma ray. And if you actually do this in vacuum, there is no way of conserve energy momentum from a single photon to electron-positron pair. But in this case, the gamma ray is sent into a photographic plate. And so it can actually interact with the nucleus inside this photographic plate. And the photon coming on top of the nucleus can create electron-positron pair by having a recoil momentum on the nucleus. So that's how you can actually excite the negative energy electron to positive energy electron, which is now viewed as a creation of an electron-positron pair. And so this was done back in 1933 by the daughter of the Madame Curie, Irène Joliot-Curie, and her husband, Frédéric Joliot. That she also received the Nobel Prize in Chemistry based on her study of radioactivity following her the career of her mother. And this is another experiment they have done to create a pair of matter and antimatter from the sending in energy. So this is clearly a manifestation of the Einstein's relationship E equal mc squared, namely energy is capable of turning into mass by E equal mc squared. So energy of the photon now turns into two rest energies of electron and positron, 2mc squared, plus additional kinetic energy C, of course, that they are moving particles in the photographic plate. So that's the first human-made antimatter. So you can really do what Sahil just described, namely to excite negative energy state to positive energy state. And the way we observe it is the creation of a particle and an antiparticle, or matter and antimatter. Okay, any questions about that? Everything okay? And that leads us to the legacy of Berkeley. We are right here. And so on top of the hill, we have this Lawrence Berkeley National Laboratory. And that's actually the first ever national laboratory in the country. And it was, of course, started with Ernest Lawrence, our former faculty member, Nobel laureate. And he decided to build a powerful accelerator on the top of the hill. So he, of course, discovered this principle of a cyclotron for an accelerator. And the first cyclotron he built is something that can sit on his palm. It was only like this big, but the cyclotron became bigger and bigger and eventually became this big that was built on the hill called the Bevatron. And Bevatron has this name from BeV, Bev, and B is billion, so billion electron volt in the energies. And a billion electron volt these days are called giga electron volt or GeV or JeV, but they used to call this BeV instead. And so this was the first accelerator that can accelerate, for example, proton beam beyond GeV energies. And rest mass of the proton is about 0.938 GeV, so it's about 1 GeV. And this machine accelerated proton up to something like 7 GeV. So that's 7 times higher than the mass rest energy of the proton. So the proton is already ultra-relativistic once accelerated in this Bevatron accelerator. And they smashed this high energy proton beam on a target. And when proton interacts with the nucleus in the target, it led to the pair creation of proton and antiproton. And in this photographic film, the antiproton is seen coming from above. That's this trajectory called L up here. And antiproton comes in, and they already know the charge from the bending of the trajectory again in the magnetic field. And of course, the antiproton was created from accelerator, so you don't need to put in a metal plate to see from which direction it came from. I forgot to tell you that in the cloud chamber experiment by Carl Anderson, he was actually detecting cosmic rays. So he wasn't clear from which way the particle came into his cloud chamber. That's why this metal plate was important. But in this accelerator-based experiment, of course, you know where beam's coming from, where the beam smashes on a target, and particles come out from the target. So you know beforehand which direction particles are traveling. So you don't need to have a metal plate to understand the direction of the particle. So you know it's coming in this way. You know how it's bent in magnetic field, so you know it's charged. So we know that this is a negatively charged particle. Unlike proton, which has a positive charge, this is a negatively charged particle. And this negatively charged particle came in and then hit a proton inside this photomagnetic field, and proton and antiproton annihilate. So that's the opposite process from what we saw on the previous slide. So on the previous slide, we saw energy, namely photon, came in, and that turned into a pair creation of matter and antimatter. In this case, antimatter came in, antimatter hits matter, and they pair annihilated into energies. And in this case, that energy turned into a new particles called pions, which seem to sort of spray out from this collision point. And this is called the star event because of that. It looks like a sort of a star that something is shining, and you see these particles coming out from this annihilation of proton and antiproton. And that's the discovery of antiproton, which earned Nobel Prize to Chamberlain and Segre. So this is one of the legacies of the Berkeley Nobel laureates. We managed to produce this antiproton for the first time in artificial fashion. And of course, this kind of reaction can happen in the cosmic rays too. So indeed, when you look for the cosmic rays, which are mostly protons coming from some the explosion of stars in the past called the supernova remnant in our galaxies, and they spray out high energy protons, and those protons would eventually reach the atmosphere of a planet. And when the protons hit some of the nuclei like nitrogen and oxygen at a high up in altitude in our atmosphere, basically the same reaction can happen, and that would produce antiprotons as well. So people now have detected antiprotons coming in from cosmic rays as a secondary particle of the collision of the cosmic ray protons in the atmosphere. So this antiproton actually does exist, but much, much fewer quantities at the level of 1 part in the 10,000s or so in cosmic rays, because they are secondaries, not the primary cosmic rays. So this is how we know the antiproton exists. And that's also a confirmation of the prediction by Dirac that spin 1/2 particle should be accompanied by its antiparticle. Okay, any questions about this?
I guess the resulting pions, are they matter particles or are they like massless excitation?
Yeah, so the pions that is seen here are charged particles with spin 0. So you have both pi plus and pi minus created in this picture, and they are described by complex Klein-Gordon field. As we talked about last week, complex Klein-Gordon field has this mode expansion and has a piece with annihilation operator for a particle and creation operator for antiparticle. So you can create pi plus and pi minus together also in pairs, and that's what you see here in this picture. Does that answer your question, Sahil?
And are the pi plus and pi minus anti-particle and particle pairs?
Yeah, that's right. Right. And which one you want to call matter and antimatter is actually, in some sense, your choice. In the case of the proton and antiproton, obviously you want to call it proton matter and antiproton antimatter because we are made of protons. And same with electron. We want to call electron matter and positron antimatter because we are made of electrons. But in the case of pions, we are not made of pions. So which one you want to call matter and antimatter is in some sense your choice. You can call it pi plus matter particle and pi minus antimatter particle, or pi minus matter particle and pi plus antimatter particle. Either way is fine. But they are the pair of particle and antiparticle pairs as described by a complex Klein-Gordon field. So that part remains. But which one you call matter is in some sense your choice.
Mm-hmm.
Is that okay?
Yeah.
All right. Any other questions on this? Good. And so this is the Nobel Prize to Emilio Segre and Owen Chamberlain. So we talked about spin. And so let us recap this. So we talked about this commutation relations between Hamiltonian and orbital angular momentum, which is not zero. So orbital angular momentum is not conserved. And on the other hand, spin is not conserved either. Only the sum of the two is conserved. So that's what you were checking with the homework problem. That's what we already talked about. So this actually leaves one problem. When you are dealing with the quantum mechanics, you used to describe a free spin 1/2 particle by specifying its momentum, and you could choose the quantization axis of spin based on your preference. and we often call the z-axis, but it doesn't have to be. So you choose arbitrary axis for quantizing spin, and whatever axis you choose, of course, spin is quantized in the unit of positive h bar over 2 or negative h bar over 2, but nonetheless, you could choose your axis. And that's because the spin commutes with the Hamiltonian of non-relativistic particle p squared over 2m. But what we see here is spin does not commute with the Hamiltonian when momentum is finite. So when momentum is 0, right-hand side vanishes. So Hamiltonian does commute with spin. And that's what you confirm in a homework problem. Namely, if you're talking about a particle at rest, you can specify spin either up or down, and you have two states with positive energies. And you also have two states with negative energies. But nonetheless, you could choose the spin axis of your choice. But when you go to the state with finite momentum, here's something new we didn't know about in non-relativistic quantum mechanics. Spin is no longer conserved. So I cannot specify a state with momentum with arbitrary spin axis. I can no longer specify spin independent of the momentum. So I need to come up with a new label of the state that would commute with the Hamiltonian when the momentum is finite. And spin is not good quantum number anymore. And what it could be turns out to be what is called the helicity, which is nothing but angular momentum projected along the direction of the momentum. So this J dot P is the selecting out the component of J, total angular momentum, along the direction of the momentum, divided by the magnitude of the momentum. So this is really the projection of angular momentum along the momentum axis. And the reason why this is very useful is that when you look at the the dot product of angular momentum and momentum vector, we know the orbital angular momentum is x cross p, which means the x cross p is always orthogonal to the direction of the momentum. So when you take further the dot product with the momentum, the orbital angular momentum drops out because it's orthogonal to the momentum. The only piece that remains in this dot product is the spin piece. Namely that this helicity singles out spin and drops orbital angular momentum. So namely that if you choose the spin quantization axis to be along the direction of the momentum of the particle, that is a good quantum number because it's made up of J that commutes with the Hamiltonian. P also commutes with the Hamiltonian because there's no X in it. So this helicity J dot P commutes with the Hamiltonian. Therefore, it's conserved. And this also commutes with the momentum as well, because it's actually in the same direction as its momentum. It singles out the spin alone, so there's nothing that doesn't commute with the momentum in here. So this helicity operator commutes with both momentum and Hamiltonian, and therefore I can specify helicity simultaneously with energy and momentum of the particle, and therefore that's a good quantum number. So I can label states of the Dirac theory by specifying the momentum and the helicity, and helicity has this meaning of the spin along the direction of the momentum. So therefore the eigenvalue of the helicity is plus minus h over 2. So what that means is that when I talk about the particle state with helicity plus h bar over 2, this is the direction of the motion, namely the momentum, and the spin is along the direction of the momentum. So what it means in terms of the rotational motion is that the spin is going clockwise as a particle moves into space. So it's like a screw. The normal screw is what we call the right-handed screw, namely that you screw the screw in by turning your Phillips screwdriver clockwise, and that's how the screw goes into the piece of wood. So this is the same direction of the spinning. So we call this kind of particle right-handed. So right-handed particle has the helicity positive, which means the spinning is clockwise as the particle moves in space. When the helicity is negative, on the other hand, you have the momentum in the same direction, but spin is pointing in the opposite direction. And then the spinning is now anti-clockwise. So the spin direction is the opposite from momentum direction. That's why helicity is now negative, which corresponds to anti-clockwise rotation of spin. So when you talk about Dirac theory, you specify the linear momentum P. And for a given linear momentum P, you have two states, one with positive helicity, h bar over 2, another with negative helicity, h bar over 2. And so that corresponds to the fact that we are talking about spin 1/2 particle. Degeneracy is twofold, spin up and down. But the new thing is that you have to choose spin quantization axis along the direction of the momentum. Otherwise, momentum axis, the spin quantization would not be conserved by time evolution of the state. So this is what we have to do when we talk about relativistic particles. We specify momentum and the helicity of the particle. And helicity is the spin angular momentum along the direction of the momentum. And for spin 1/2 particle, helicity takes values either plus h bar over 2 or negative h bar over 2. We call them right-handed spin 1/2 particle or left-handed spin 1/2 particle. And the right-handed corresponds to clockwise spinning, and the left-handed corresponds to anti-clockwise spinning. So this is how you can specify a state for a relativistic particle species. We didn't have to face this question for Klein-Gordon field because it didn't have spin. But now that this particle has spin 1/2, we face this problem. And the answer is we can specify momentum and helicity as commuting simultaneous observables, which are good quantum numbers to specify a state. And in the case of the photon, we use helicity 2. In this case, spin is 1, and helicity is either plus h bar or minus h bar, very similar to spin 1/2. And they correspond to circular polarization of the photon. And we talked about this before when we quantized the vector potential. And you can specify linear polarization in either direction, or you can specify two circular polarization by taking linear combination of them. And now we see the context of it. So for relativistic particles, you can specify helicity along the direction of the motion. And for case of spin 1/2, helicity is plus 1/2 h bar or minus 1/2 h bar. For the case of spin 1, the helicity is plus h bar for right-handed circular polarization or negative h bar for the left-handed circular polarization. It's the same idea. Okay, so any questions about this concept of helicity? This may be first time you see this idea of the helicity for relativistic particles.
Just like a quick thing, so if the spin is quantized along the direction of the momentum,
Mhm.
how do we obtain this helix like rotation along this axis?
So if you imagine using a different quantization axis of spin, then this commutation relation tells you that spin is no longer conserved. So this is, in some sense, Heisenberg equation motion for the spin operator. And spin would precess around the momentum. So if you try to quantize spin, let's say perpendicular to the momentum direction, it doesn't stay that way. It starts to really go around like this. And that's what this commutation relation is telling you. So that's why I cannot specify spin as a conserved quantity to label a state because it doesn't stay constant, but you can see the spinning motion happening. So that's the meaning of the spinning clockwise or anti-clockwise. If you try to use quantization axis perpendicular to the motion, But if you use the coordination axis along the motion, then it stays put. It doesn't change anymore. And it stays left-handed forever or stays right-handed forever. So that's the idea of the quantization axis. Am I answering questions, Akhil? I wasn't totally
Yeah,
sure.
just like the correspondence between like what defining along a predefined axis, and then course making the correspondence between that and defining it along the momentum axis as we should. Okay.
So that if you have some spin not perpendicular but has two components, for example, then projection on the direction of momentum stays constant, but perpendicular piece rotates. And that's what this equation is telling you.
Oh, okay. That makes sense.
Okay.
We still quantize along that axis. This is just in the case that say we don't, but in this case we always.
Okay. Right. So it's not a good label for state because the spin quantized and not away from the momentum axis is no longer conserved. Okay. Any other questions here? Is everything okay? Getting used to this Dirac equation? I hope. Good. So now we are talking about the finite momentum. We know what quantum numbers we use to specify a state. So what we are looking for is then full solution to the Dirac equation for a definite momentum and definite helicity, now that we know we can specify both. So we would like to solve Dirac equation with a finite momentum now. We have done this with a zero momentum so far. Now we'd like to do this with a finite momentum. And now that we are looking for the helicity eigenstate, that basically corresponds to the eigenstate of sigma dot b. So sigma dot p is spin times momentum up to a factor of h bar over 2. So and sigma dot p is simply a matrix, 2 by 2 matrix. So let's solve for the simpler problem first, than talking about the 4 by 4 matrix right from the beginning. So we now solve for the eigenstate for this 2 by 2 matrix sigma dot p. For this purpose, it's convenient to write the momentum vector in the spherical coordinate with the polar angle theta and azimuthal angle phi in the usual way. Then you can find a eigen solutions for the sigma dot p 2 by 2 matrix. So this chi is a two-component vector. And in the case of the spin 1/2 particle, we don't call this vector. Actually, we call that spinner because it's a sort of a column vector, but it has to do with a spin. So we call that spinner, and that's the terminology in the Lorentz invariant quantum field theory. So this chi is a two-component spinner now, which is meant to be the eigenspinner of this 2 by 2 matrix sigma dot p. And the eigenvalue is plus minus p. So that's because sigma dot p, if you square it, again, using this commutation relation, anti-commutation relation among Pauli matrices we talked about, 2p's commute, so commutator piece vanishes, so sigma dot p squared is nothing but p squared. That's the magnitude of momentum squared. And then sigma dot p is square root of that, so you can have two eigenvalues of plus or minus the magnitude of the momentum vector. And then you can write this out very explicitly. So the eigenspinner, the two-component eigenspinner with the positive eigenvalue is written this way. And you see the polar angle with a half in it. And this is a sign that we are indeed talking about something of spin 1/2. And the eigenspinner with a negative eigenvalue is this one, again comes with theta over 2. And you can also see that they are orthogonal to each other when you take dagger of this, and you have to complex conjugate this one here, and they take the product with this one, then the product of upper components and product of the lower components cancel against each other, so they are orthogonal. And they are also correctly normalized. If you take chi plus dagger, chi plus, that's a cosine squared theta over 2, plus sine squared theta over 2. This phase cancels with a complex conjugation, so it's correctly normalized. So these are the eigenspinors of sigma dot p 2 by 2 matrix. So now that we know how to diagonalize this 2 by 2 piece, using these eigenspinors, this sigma dot p now becomes a number plus b or minus b. Then this Hamiltonian is regarded as a 2 by 2 matrix. Then solving problem for 2 by 2 matrix is a lot easier than solving problem for the 4 by 4 matrix. Then you can come up with eigenspinors of the full 4 by 4 Hamiltonian. And that's what we're going to do on the next slide. So that's the approach we take, namely that Hamiltonian is 4 by 4 matrix, and that's hard to solve for the eigenstates. But because we know we can specify helicity, which has to do with the sigma dot p, we first focus on the sigma dot p 2 by 2 matrix, and we solve the eigenproblem of this 2 by 2 matrix, and we found the eigenspinors for that. And using these eigenspinors, this 2 by 2 matrix sigma dot p now becomes numbers plus b or minus b. Then the Hamiltonian can be viewed as a 2 by 2 matrix now. And solving the problem for 2 by 2 matrix is a lot easier. And that's how we get, in the end, the full 4-column eigenspinor for the Dirac equation. Okay, any questions about this? Everything okay? All right, so now we solve for the Dirac equation with a full momentum dependence. The first thing we look for is positive energy solutions. And positive energy means that we're looking for a solution with the usual time and spatial dependence. So this Q dot X, this Lorentz invariant inner product, is minus I energy times T plus I momentum dot possession vector. So that's this Q dot X combination. This is the usual time and spatial dependence with the positive energy and the momentum vector P. And so this P in a Hamiltonian was meant to be the derivative operator. And in order to avoid the clash of notation, I'm using Q for the full momentum of the solution we are looking for. So this Q is meant to be numbers, the full momentum vector of a definite numbers. And the P is the derivative operator in this expression for the Hamiltonian. So the P derivative operator would extract eigenvalue Q from this wave factor. So that's why I'm using Q instead of P for the sake of this slide. I hope that's clear. So when you act this Hamiltonian operator on this psi solution, then this P derivative operator is replaced now by its eigenvalue Q. So this now becomes a simple 4 by 4 matrix. It's no longer an operator. And using chi plus solution we worked out on previous slide, then this sigma dot Q turns into positive Q magnitude of the momentum vector. If you use chi minus, then this sigma dot P, which is now replaced by Q, turns into negative magnitude of Q vector. And that's because of these eigenvalue solutions we looked at. So using chi plus, I'm supposed to solve the 2 by 2 matrix problem where the off-diagonal piece is positive Q times C. If I use chi minus instead, I'm supposed to solve this 2 by 2 matrix problem with negative Q times C. And that's an easy problem, just a 2 by 2 eigenvalue problem. And so the solution turns out to be this. When I use chi plus, in order to diagonalize this matrix, I'm supposed to put the square root factors E plus MC squared for the upper two components, because this is two-component spinor, and square root of E minus MC squared for the lower two components. Again, chi plus is a two-component spinor. And altogether, this is the now full component, four-component solution as an eigenspinor of this Hamiltonian. In the same way, if you use chi minus, then you find this solution that, again, the upper two components come with square root of E plus MC squared. Lower two components come with E minus MC squared. But now there's a relative minus sign because off-diagonal component has a minus sign for the U minus solution. And you can go back to the situation when particle is at rest. And when particle is at rest, energy is just purely mc squared with no kinetic energy. So the lower two components vanish for both helicities. And the upper component has square root of mc squared plus mc squared. So that's just a multiplicative factor of square root 2mc squared. And chi plus has this combination of cosine theta over 2 over sine theta over 2. And when you use the momentum vector in the z direction, then chi plus is 1, 0. And that's the solution you find in the homework problem, 1, 0, 0, 0. When you take again the z-axis, the chi minus is 0, 1. So that's a solution of 0, 1, 0, 0. That's the other positive energy solution. And now the momentum is chosen along the z-axis, but you take the limit of momentum going to 0. You have specified the spin along the z direction of up or down. And that's the way you see that these solutions indeed corresponds to particle at rest with spin up or spin down. And that is the positive energy solution. So when the particle at rest, we recovered what we looked at before, that 1, 0, 0, 0 is a solution with energy being mc squared with spin up along the z direction. 0, 1, 0, 0 is a solution of particle at rest with energy mc squared with spin down along the z direction. And these are the two positive energy solutions you have found in the homework problem. So these are the two positive energy solutions, but now with finite momentum q, they have either positive helicity or negative helicity. And these are the solutions we use in mode expansion of the Dirac field. Okay, so here I'm done with the positive energy solutions. Any questions about this?
Just a quick question. What was the relevance of the gradient operator, like the discussion for that in terms of, I guess, getting the eigenvalues?
Yeah, so if you go back to how we came up with this Hamiltonian, and that's of course the discussion Dirac did, right? So this is Dirac's discussion. Then he wanted to come up with an equation that is first order in time derivative because he wanted to maintain the probability interpretation, which required that equation also has to be first order in spatial derivative to treat space and time on equal footing. So this P was meant to be a derivative operator. So if you actually write down this equation, whenever I write P here, that was meant to be this derivative operator in space. So the Hamiltonian we are talking about is this right-hand side of this Dirac equation. So when you write C alpha dot P, P was meant to be H bar over I times gradient. So this piece here is H bar C over I times gradient acting on psi. So that was the meaning of the Hamiltonian. So when you solve for the eigen solutions for the Hamiltonian, that's what we are trying to do up here. And maybe it's faster if I actually switch back to this mode and scroll down to here. Then I had to remember that this P was meant to be this derivative operator. And so I wanted to keep the notation separate between this derivative operator and the eigenvalue Q as a number. And that's why I'm using separate symbol P and Q for the purpose of solving the eigensolutions for the Hamiltonian. Does that answer your questions, Hill?
Yeah, so I guess when we're looking for eigensolutions, the P operator just becomes the P vector.
Right, that's right. But the reason I'm actually using different notation here, and if this is the only solution we're looking at, then we could have actually used a P as a notation too, as an eigenvalue. But when you solve for the negative energy solutions, and it's awkward to talk about negative energy, so I'd rather keep Q vector always that corresponds to positive energy. So negative energy solution would correspond to putting a plus sign here instead. But if you do that, then this derivative operator would pull out negative Q from this wave factor. And that's what I'm going to do on the next slide. So for positive energy solutions, in some sense, I don't care. I could have labeled this Q as P. But when I talk about negative energy solutions, I'd like to invert the sign in the exponent. And then I have to distinguish P as a derivative operator from its eigenvalue negative Q in that case. And that's why I'm using two separate notations to avoid possible confusion later on. And that's what I'm going to see on the next slide.
Mhm.
Is that okay?
Yeah.
Okay. Any other questions? People are quiet today. What's going on? No further questions? Sure. Okay. So now we dive into negative energy solutions. So as I already said in response to the question from Sahil, this is meant to be derivative operator. But now for the negative energy solutions, I like to put a plus sign here so that I can maintain the time component of Q4 vector to be positive. But because of the opposite sign, this is meant to be the negative energy solution. But because of this opposite sign here, when I act this derivative operator P on this exponential factor, that will pull out the eigenvector, but now with the opposite sign. So that's why I'm keeping P and Q with separate symbols. So P is still meant to be a derivative operator, but its eigenvalue turns out to be negative Q. So I need to substitute negative Q into derivative operator P in this 4x4 matrix to look for eigen solutions. We again use these two component solutions as an eigenvector or eigenspinner of this 2x2 sigma.q matrix. So we know these solutions. But we have to be careful about the minus sign I got for Q. So for positive helicity chi plus solution, then off-diagonal component is actually negative Q instead. And for the negative helicity solution, then I need to put positive Q in the off-diagonal component of this 2x2 matrix. So that affects the relative sign between upper two components and lower two components of the eigensolutions. And remember, we are looking for this negative energy solution, and I'm keeping this symbol E to be always positive to avoid confusions. So negative E is negative, and therefore this would be the eigenvalue for the negative energy solutions. So that's what we are looking at right now. And the solution can be worked out explicitly. So for the positive helicity, because off-diagonal component is now negative, I have this negative sign in here. And for negative helicity solution, I don't have the relative negative sign between upper two components and lower two components. And unlike the case of the positive energy solution, when you approach zero momentum, where energy becomes mc squared, upper two components vanish, and you have only the lower two components. And that's, again, what you saw in the homework problem. For negative energy solutions, you have only lower components. And this is, again, 1, 0. So this is the four component 0, 0, 1, 0. That's one of the positive and negative energy solutions. And chi minus, when the theta is 0, is 0, 1. Therefore, I have a solution 0, 0, 0, 1. And that's the other negative energy solution addressed, as you see in the homework problem. So this is the complete set of solutions. I have two solutions with positive helicity and negative energy with positive energies. And I have two negative energy solutions, one with positive helicity and negative helicity. And negative energy solutions have to be occupied, so they represent the antimatter solution to the problem. And therefore, at the end of the day, I have 4 degrees of freedom in the Dirac theory. Matter particle with spin or helicity, positive and negative. An antimatter particle with helicity positive or negative. Altogether, there are 4 states. 2 particle states with both signs of helicities, and 2 antiparticle states with both signs of helicities, hence 4 degrees of freedom. So that's what the content is of the Dirac theory of spin 1/2 particle. Okay, any questions about these negative energy solutions?
When
No?
you refer to like the entries as 100, I guess the combinations, could you, I guess, just clarify that? Just for like, I guess, one specific case.
Oh yeah,
not,
sure,
not all.
sure. So let me go back to the positive energy solutions, which is because this is, I'm sure, easier to understand. And these chi spinors are 2-component spinors, and Hamiltonian is 4x4 matrix. So the solutions are 4-dimensional column vector or column spinor in this terminology. So the way this is 4-dimensional is that chi plus is already 2-component. So this is the first component and second component is represented by this expression square root E plus MC squared times chi plus. So this is the first component and second component. And this E minus MC squared square root chi plus is the third component and fourth component out of this 4-component spinor. So when I say 1, 0, 0, 0 for the particle at rest with spin up in z direction, what I'm referring to is that this chi plus is 1, 0 as a 2-component spinor. I plug in 2-component spinor here and there. So I have 1, 0 times square root 2mc squared. So that's the first component. Second component vanishes. I have, again, 1, 0. But this E minus mc squared vanishes when particles at rest. So the third component vanishes. Fourth component vanished from the beginning of sine theta over 2. So that's what I meant by 1, 0, 0, 0 for the particle at rest with spin up. And same here with chi minus. So when the momentum is a z direction, chi minus is 0, 1. And I put the 0, 1, 2-component spinor in here. So I have square root 2mc squared times 0, 1. The first component is 0. Second component is 1 times square root of 2mc squared. And the third and fourth component, again, is 0, 1, 2-component spinor. But that's multiplied by 0 when energy is mc squared. So the third component vanishes. Fourth component vanishes because of E and mc squared canceling. So that's what I meant when I said 0, 1, 0, 0 as the particle at rest with spin in the negative z direction. Does that answer your question, Sahil?
Yeah, so we just chose the polarization of the momentum vector such that theta is 0, and hence we get.
That's right.
Yeah, I guess I just didn't realize that part.
Okay.
Yeah.
So the way I argued about this is that I first chose the momentum direction along the z direction, so theta vanishes, and this is 1, 0, this is 0, 1. Then took the limit of momentum going to 0 so that you get the particle at rest. And initially, you define the spin quantization axis along the momentum axis, which I chose to be the z direction. So as a limit, I find particle with spin along the z direction. And that turned out to be 1, 0, 0, 0. Or when you start with a negative helicity particle and take the limit of momentum going to 0, then spin's pointing backwards in z direction. And that's the solution of 0, 1, 0, 0. So I use the momentum axis to quantize spin along that direction, but taking the limit of momentum going to 0, that ends up being the quantization axis of the spin at rest. And that's how I recover spin up and spin down for particle at rest. So that's the process I described to you. Does that make sense?
Yeah, definitely. Thanks.
Okay, good. And I did the same thing for the negative energy solution over here. So initially choosing the quantization axis along the momentum, which I take to be z-axis, then 1, 0, 0, 1, just like in the previous case. Then the solutions at rest turns out to be 0, 0, 1, 0 and 0, 0, 0, 1. And that's how you recover what you are seeing in a homework problem for particle at rest with spin up and down along the z-axis. Okay, any further questions on these negative energy solutions? Okay, good. And this is just a reminder of what we have done in non-relativistic Schrodinger field theory with the chemical potential or Fermi momentum. And what we did is, okay, to describe states where all these energy states are occupied up to a Fermi energy mu. Then we can talk about states occupied as the ground state and state vacant as an excited state. So instead of talking about initial creation operator B, I can now flip B in terms of D dagger, because annihilating a particle is a creation of the whole. And B dagger by PD, namely that the creating a particle would be removing the whole. So if you have a whole already, if you create a particle here, that's the same thing as removing the whole. So you basically interchange the roles of creation operator and annihilation operator. And that's how we came up with a theory of the whole in non-relativistic theory. And what we have to do in this relativistic theory is draw the line of the Fermi energy at exactly 0. So all the negative energy states now have to be occupied to come up with a well-defined ground state, because by occupying the state, you lower the energy. So you rather lower energy or by occupying all of the negative energy states, and that's how low as you can get. And keeping all the positive energy states unoccupied, which is taking the Fermi energy to be at 0. And that's exactly what we do with the Dirac theory. And that is in the end, is what avoids the decay of a particle decaying into the negative energy states. And so what we have to do is exactly the same thing as we have done in the Schrodinger field theory. And here I'm now writing the P as the derivative operator, because I'm no longer doing the Dirac idea of regarding as the quantum mechanical equation, but this is a field equation now. So this is now a explicitly spatial derivative. I don't write this as P anymore. And then I do the mode expansion of the field psi using the negative and positive energy solutions and negative energy solutions. Notice that here I have minus sign correctly for the positive energy solutions and plus sign correctly for the negative energy solutions, and introduce the annihilation operators E and A and B for positive energy solutions and negative energy solutions for either helicities plus or minus h/2. But now the idea of occupying all the negative energy solutions is achieved by replacing this negative energy, the annihilation operator, by the creation operator of the wholes. So instead of writing this as A and B annihilation operators, I now write this field operator in terms of the expanded in modes with annihilation operator for particles and creation operator for the antiparticles. So this would be the correct mode expansion, which is exactly the same idea as what we have done before for the non-relativistic case. And these creation annihilation operators satisfy the same the anti-commutator as the Klein-Gordon field. It is anti-commutator though, because it's a fermion instead of boson. And so you have the same anti-commutation relation for both particles and antiparticles. And all the other combinations anti-commute, namely the anti-commutators vanish. So that's how we define the Fock space. So now we define the vacuum or ground state by annihilating them with the annihilation operator for particles, and also annihilating them with the complex conjugate of this D dagger annihilation operator, And then you find a state where all the negative energy states are now occupied. And that's the ground state of this system. So that's the idea of this Dirac field, quantized way, named that this is now the quantum field theory based on originally Dirac's idea, which was a wrong idea at the end of the day, but turned out to give us something useful, namely a correct quantum field theory of spin 1/2 the relativistic particles. Okay, so I stop here. Any questions about this?
Should the momenta be reversed from V to D dagger?
That's a good question. So, when we wrote this negative energy station solution with IP.x, we sort of already anticipated that we're going to actually revert the momentum. So, as you remember, we discussed just 2 minutes ago, the eigenvalue of this derivative operator is actually negative p, now that I'm using notation p. So this annihilation operator actually carries negative p momentum. So that's why this now whole operator, D, I didn't have to reverse P because I already have reversed the definition of P when I wrote this down by anticipating it. So that's why I don't have to put negative sign over here, because in some sense, this was negative P to begin with.
Okay.
That's an excellent question. Thank you for asking. Any other questions?
On the last slide, like when
Okay.
we chose the full potential equal to 0, could we also choose it equal to any number that's like greater than the highest negative energy state, but lower than the lowest positive energy state?
In principle, yes. So you could have chosen, for example, mu anywhere between plus mc squared and minus mc squared. But it turns out that when you choose chemical potential away from 0, you can put that into your Lagrangian, but then it actually violates Lorentz invariance. So in order to come up with Lorentz invariant theory, you need to keep mu exactly 0. And in some sense, when you do Lorentz transformation, the mu can change its sign. So the only thing that's invariant is 0. So that's the reason why you have to take the mu is being 0, and that's a requirement of Lorentz invariance. And I'm sorry, I misspoke. Under Lorentz transformation, mu doesn't change sign, I apologize. But mu transforms as a 4 vector. And that's because the mu chemical potential is supposed to multiply the number operator. And number operator is a time component of the 4 vector. We talked about this before. So mu itself is supposed to be the time component of a 4 vector. So it changes from one reference frame to another if mu is non-zero. But if mu vanishes, then as a 4 vector, it's completely 0. And under Lorentz transformation, 0 vector goes to 0, and hence it's invariant. So that's why the Lorentz invariance requires the chemical potential vanishing. Does that answer your question?
Yeah, thanks.
Okay, thanks for asking that question too. It's a good clarification. Any other questions? Good. So now that I have only 4 lectures left, the first thing we will do next week is to talk about some variants of spin 1/2 particle called Weyl fermion and Majorana fermion, which appears also in condensed matter physics. I'd like to talk about that. And then talk about trying to put everything together. And by developing perturbation theory with now fully relativistic quantum field theory, we come up with this idea called Feynman diagrams in developing perturbation theory. And we do some simple computations of some processes using Feynman diagrams. So that's the plan for the rest of this course, this semester. Okay, so have a good weekend and see you next Wednesday.
Thank you.
Thanks.
Bye. Thank you, Reggie.